What questions do you have, my dears? I was going to say, you said the piecewise, so I'm assuming 7 and 8.
And then can you just do one of the other ones?
Okay, but both of the piecewise, you can't do mean value theorem on because they're not continuous.
You should have told us that.
Well, but look, part A says state whether or not the function satisfies the mean value theorem.
Oh, because it's...
So is it continuous and differentiable on its interval, on a closed interval? So if you look...
Well, it's not because there's two different functions.
Well, but it could be, but how do you test continuity on a piecewise? Because these are both continuous on their own, but then at the point where they hook together, is that continuous or no, or does it jump? So how do you tell?
I thought it would be continuous in the straight line.
Okay, that doesn't, because think about it. Let's think about this. This one, one of these does not have a line under it. Which one? This one does not.
Oh, okay. Well,
okay. So here, though, there would be an open dot at cosine pi over 2, right? What's the cosine of pi over 2? I'm at the top of the circle. 0, right? So this one's got the point. So whatever else this graph does, we know what cosine looks like, right? But at pi over 2, so here's a half of pi, it's 0 and it's an open dot, right? So it's going to do something like this because this is at 0. So here's the first part. Now the second part is sine x, and remember sine x is doing something like this, right? But from here to here, so at this point right here, sine of pi over 2 is what? So again, up at the top, what's the sine of pi over 2? Y'all can do this. What's the sine of pi over 2? 1, right? So this point is pi over 2, 1. And then this curve continues on, right? So can you use mean value theorem there? No, because it's jumping, right? It's not continuous. So you don't have to do part B because there is no part B because you can't use MVT. Does that make sense? Same thing happens on 7. It's not continuous at that break. It jumps. Does that make sense, everybody? Everybody okay? Y'all ready to do some more then?
Are the solutions on the screen?
Yeah. I'm going to set up my scenario. I'm going to do a little bit more with MVT, and then I'm going to jump into antiderivatives today, because those are fun. Yeah. Okay. These will be easy today. It's setting us up for integrals, which means we're almost done with the first half of calculus. Isn't that exciting? No, we're just on 4.2, but it's just, I'm talking about the whole course, the whole first half of the course in general, like all of calculus. Okay, Madison jumps on the interstate. I'll try my scenario. Okay. She jumps on the interstate. She drives on the interstate. Over the course of 2 hours, she travels 147 miles. And let's say she starts from a dead stop too. She gets on the interstate, she's at a dead stop. Start clocking her at a dead stop. And some police officer sees her when she gets on. And then she gets down 147 miles down the road, and another police officer calls and says, I just saw, what kind of car you drive? I just saw this little Nissan come down here, 2 hours later, whatever. Anyway, somehow they figure out 2 hours later she's tripping. Okay, so my question is, if the speed limit was 70 over the course of this entire trip, did she ever speed? She started at 0, so she got on the interstate at 0 hours, and she's going 0 miles per hour, right? And then she could have sped up, slowed down, sped up, slowed down. Can you conclude at any point over the course of this time, and she never stopped, she was going continuously, did she ever go over the speed limit?
Well, you could say yes or you could say no.
Okay, justify your answer. You're exactly right. At one point, at some point on there, right? All right, if she never stops, she's going. She can slow down and she can speed up, right? But over the course of 2 hours, she covered 147 miles, right? So on average, what was her average rate of speed? (147 over 2), which is 70 what? What?
She's probably going to be the slowest moving person.
Yeah. So, but that's her average rate of speed. What if she slowed down? What if she slowed down and sped up? Why?
I mean,
How?
She could have gone up to like 100 if she just went.
But at some point over this course, she had to hit this speed. She had to. And that's what mean value theorem tells us. Is because it was continuous, a closed interval. This is a rock, right? At some point over the course, her instantaneous speed had to hit this at least one time. Does that make sense? Isn't that cool there? Oh, okay, y'all. Yes, just say yes. Just pass it by me. That's exactly right. That's exactly right. So your homework has one that this is the, and I'm not going to work it with you because it's the only one like this, and I love this one like this. But a trucker handed in a ticket at a toll booth showing that in 2 hours she covered 159 miles on a toll road with a speed limit of 65. The trucker was cited for speeding. Can you justify it? It's 60 right there before Sand Hills, like, but 65? I don't know. Okay. So the point is that over the span of time, if you take your average rate of speed, then some point over that span of time, you had to have hit that average rate of speed at least one time. And if that's over the speed limit, then you sped at one point. Does that make sense? That's the mean value theorem in a nutshell. That's the most applicable way I can tell you. Yes? No? Maybe so? All right. Let's then talk about, no. I think I'm going to leave the word problems for you to struggle through a little bit. Because there's only a couple. So let's jump to antiderivatives. And they're going to all use that same premise of that mean value theorem. It's the same section, but a different type of lesson. This is fun. If this is my function, what would the derivative be? But what if I started here? Could you come up with the original function? Not with that 7. That 7's throwing off, right? That's throwing you off. Could you come up with at least this part, though? Yes. Okay. That's called an antiderivative. But when we do it, what we're going to do, derivative. Because that function is what's throwing, and the reason for that is, what's the derivative of a constant? 0. So this 7 could be any constant in the whole wide world if I started here. Do you agree? So we're going to, for our antiderivatives, I'm going to give you a derivative, and we're going to work our way backwards to find the antiderivative, but what we're going to have to do is we're going to have to throw a constant on the end of it, because any of them could have any constant thrown there because the derivative of a constant is 0. Okay? So we're going to have a plus C. You can't remember on that little song, do y'all remember, don't forget your plus C? Or don't forget to add a constant? So, but anyway, this is what they're talking about because we have to have. You didn't see the calculus rhapsody when we did it? Yeah, they did say a lot. All right, let's do an example. Let's say the derivative is we'll start easy. What's a possible antiderivative? And I say possible because there's an infinite number of antiderivatives because that constant can fluctuate, right? So what is a possible antiderivative here, and how are you coming up with it? Okay, tell me what you're doing. Okay, when we go from function to derivative, if I'm talking about the power rule, remember this becomes this, right? But if I'm going from derivative to function, my power rule is the backwards of that, right? So if it is x to the n, what are you doing? So you're doing 1 over n, because you're dividing by n, right? And you are adding 1 to the exponent. No, it's just the n. Right? No, wait, I have to do it. I have to look at it. This would be, yes, it is. So this is going to be what? 3x squared, right? Minus 2x, finish it, plus a constant. It could be, but if I put plus a random constant, then my constant could be positive or negative. Right? Excuse me. I love it. Sorry about this, y'all. I have to think about it in a minute. You're going to start getting so confused. To me, this is the hardest thing, is remembering when do I add or subtract and when do I do what. Okay, so yeah. Does that make sense? Because I'm fixing to kick it up just a little bit. Okay. You talking about those little corn dogs? You're not the only person that's been asking about those. You got that? Yeah. Give me an antiderivative. And be very careful on this one. This is f of x. Oh no, yeah, f prime, sorry. I want you to find f of x. Find the antiderivative. It is. Why is it negative cosine? But don't forget, plus a constant. Every time you do an antiderivative, it's plus a constant. Okay. Let me show you a little bit of a new notation, and then I'm going to add a little something to it. We have function, right? We can take the derivative, second derivative, the third derivative. We could keep going, right? But what if I started the function and I asked you to find the antiderivative? There's also a notation for that. So if I start with an original function and I go backwards, I denote that with a capital F of x. That tells me that it's the antiderivative of f, okay? They do use this notation often, so make sure you understand that is.
Say that again?
So see how I started? I put f of x,
Yeah.
but then y'all were like, is that the derivative? I was like, yeah, okay, let's call it the derivative. Because I'm asking you for the antiderivative, so I'd be asking you for f of x. If I gave you f of x like this, and I said, what's the antiderivative? The antiderivative would be capital F of x. It's just the notation and the manner that it goes, the order. All right, let's try it out.
So all this.
Let's say.
What if it was, what if you like 2 layers?
Depends on where you start. I don't know. You would have to have, and we're fixing to do that. You would have to have. So how could I figure out what that constant value needs to be? What do I need to have? Information. What kind of information? What if I had a point on the function? Would that be enough to find the c? Sure, for sure. For sure it would. So let's take this same function here, and let's say that the function passes through the point 0, 2. Now I can find a specific antiderivative, and I wouldn't need the c in there, right? And notice I said the function passes through, so not the derivative, but the function itself. So that's this one, right? So I'm going to plug that in. So f of 0 better give me 2, which means that negative cosine 0 plus c needs to be 2.
Oh, okay.
Well, what's the cosine of 0? 1, but it's negative, right? So negative 1 plus c is 2, so c's got to be. So what is the antiderivative here? The constant is 3, so it's negative cosine x plus 3. Does that make sense?
That does make sense. Actually, kind of like that.
I told you this wasn't that is fun. Shut up, it's fun. I'll do one from your homework. Just one, then I'll let you do your homework. Okay, so some of them aren't like, let me show you, for instance. Some of them you have to think about, like that pink sheet of derivatives and what derivatives look like. Let me show you what I mean. And we won't get into like backwards chaining and stuff just yet. Right now, this is number 37. Well, because you have to kind of think about that, right? What if you chained it when you took the derivative? I got a little domain restriction here, but that's just because of my denominator and the function that I'm going to get. Let's say that it passes through the point negative 1, 3. Again, this is number 37 on your homework. Find the function with the given derivative that passes through the point P. See if anybody gets this. Look at it and see. Did you look? Did you cheat? Did you get that quick? What did you just say? It is ln. That's amazing, Brian. I don't know. Maybe you're looking at you answers or something. I was trying to trick you.
No, Brian, you're amazing.
No. I didn't expect anybody to get it. Not because it's Brian. I just didn't expect anybody to get that. Looking at because we've just done power rule. We didn't look at that. What clued your brain in that was ln? It's 1 over something. No, I didn't. I really didn't. I didn't think anybody was going to get it. I thought you had the solutions pulled up or something. That's awesome. That's awesome. I wasn't being like
That's
that.
like when Carter was.
It is ln, and it's ln because the derivative of the natural log is 1 over that that argument, right? And I got to do the plus c. But now finish it. I'll finish it. Because it goes through this point. Yeah.
What is x greater than negative 2?
It's just a domain restriction because once you get here to the function, you can't have anything negative in this argument because that wouldn't work. You can't take the log of a negative number. So it was just giving you the domain to begin with.
You just said it like a
I got 3 for C. Is that what y'all got?
Well, what is ln1?
Yeah. So f of x, my antiderivative here, and this is the antiderivative. It's not an antiderivative because an antiderivative could have that plus c. I could have any variation of c on there. But the antiderivative goes through a specific point, that point being negative 1, 3, and I would get the natural log of x plus 2 plus c. Well, the reason is whenever you get to the original function, you can't take the log of a negative number. But it's not impacting how you solve it all. All right, what do you think? Okay.